Okay, class, so let's solve this problem on laterally supported beam analysis. So we have here the figure, and it is actually a simply supported beam problem uh, using a W16 by 31 A992 steel loaded, no, as shown by the service dead load and the service live load. Okay, so we are just asked to find the, or rather, we are just asked to check if the beam has adequate moment capacity or strength, no, to withstand the load. Okay, so this is a continuously laterally supported beam, so we will be using the procedure I just discussed a while ago. Okay, so the first thing when you are dealing with sections, of course, is to get its property. So if it's a rolled section, you just look into your table and uh, list down all the possible properties you will be needing. No? So what I did is I get the whole sectional properties of the W16 by 31 and place it here. No? Okay, so para magamit natin. Okay, so there's no lateral torsional buckling or LTB involved because your beam is said to be laterally supported all throughout or continuously laterally supported. So all we have to do is to use the procedure on the compactness and check it in order to determine the moment capacity. Now I'd like to show you the table uh, on the compact section property or criteria. Meron siyang given na dito, ano, na BF over 2TF tsaka H over TW. So you can use this directly, or if this is not available to you, you can calculate it on the basis of the given value of BF and TF and also your H over TW. No? And sometimes the exact value is not the same, pero may konting discrepancy due to the rounding of units. Okay? Okay, for the first step is on the checking of the compactness, we need the table for unstiffened and stiffened values of your lambdas of P and lambdas of R. And we take note that lambdas of P is always less than lambdas of R here. So we might as well check compactness first before we check on the lambda R limit, no? Ito muna, pag pumasa siya dito, sigurado pasado siya dito, no? Because this is always less than lambdas of R. And take note that the value for unstiffened and stiffened are different. And this is for flanges, these are for webs, no? Okay? So ito yung ating comparison, no, na gagamitin on our compactness check. Okay, so let's use it. For the flange, we have here the value BF over 2TF, which is 6.28 from the table. So I just got it from the table there. And H over TW is also from the table. And compare it with the lambda P. Okay, so this is your lambda P flange, which is 0.38 square root of E over Fy. I substitute the value of E and Fy, A992. So this becomes 9.152. So since this is less than this one, our conclusion is this is compact. which means to say that we have no problems on the compactness of your flange. Okay? And also for your web, which is the stiffened part, we simply compare 51.6 your h over tw with that of the lambda p w by substituting again the value of e and fy on this formula. We now compare 51.6 less than 90.53. Therefore, the web is also a compact web. Okay, and take note of this. The AISC gives us values for compactness on the web for all shapes on which your Fy is less than 65 KSI. So lahat ng shapes daw ginawa ng AISC to be compact, no, as far as the web is concerned. So if you are using an Indian table, an Indian code, or a Canadian code, a different code, this will not be the case, no? This is only true for the AISC code. And this note will help us reduce our computational step by trying to be confident that always the web is not critical in terms of compactness. So if you look at the graph of m versus lambda, we take note that your bf over 2tf and h over tw falls less than your lambdas of p requirement. So this region will give you now a conclusion that we are going to use the compact formula in order to get the capacity of your beam, no? So if you will look into now our lecture a while ago, we have to use this formula, compact section, in which MP is equal to ZFY, to come up with our nominal moment MN. Okay? So ito lang yung gagamitin natin. And lucky enough, the Z is already given in the table also, so we don't have to compute for it. Okay, but in case there's no available table, again, all we need to do is to use our basic knowledge on how to compute for your plastic modulus for us to be able to compute the nominal moment. Okay, so Z is equal to 54 from the table, so Fy is 50. So this 12 here is a conversion factor from inch kip to foot kips. No? So our value now becomes 225 foot kips. Remember that our standard configuration for your wide flange beam is always at the strong axis of bending. So your Z must be the ZX, not the ZY. Okay, and we compute for the actual moment on the basis of the service load, dead load, and live load, which is given. Of course, in the dead load, we have to add the self weight, no, of the beam itself, because it does not include the self weight yet. So for a W16 by 31, the self weight is 31 pounds per lineal foot converted to KLF. So we simply add 0.031 to 0.45 and then multiply it by the factor 1.2, and for the live load, we simply multiply the given value to 1.6 to get your ultimate factored load. So this is the load combination we are going to use, no? The other load combination, 1.4 dead, is actually not critical. So this is not a critical combination. So the governing load combination is this one. Take note that always this will govern compared to this load combination when your live load is less than 8 times the dead load. Okay? So wag ka na mag-compute kung yung live load mo is less than 8 times the dead load. Always use this load combination. Of course, if the wind load and the earthquake load are given, you have to consider the combination involving the earthquake and the wind load. So for a simply supported beam, your MU is WUL squared over 8, and this is now computed to be 163.95. And there's a missing step here. We have to compare always the ultimate load, factored moment rather, with that of your moment capacity PMN. So I have to multiply this 225 with 0.90, which is 202.5, to find out whether the beam can support the needed loadings or not. No? So it happens to be greater than 163.95, and therefore your beam as presented on this problem is safe to resist the given loading. So that is a very simple presentation on how to use the principle of compactness in investigating the adequacy of a beam section. Okay, so thank you very much. If there are questions, I'll address your concerns afterwards. Thank you for listening.